Hi, this is Usman Ali from University of Connecticut, and I am presenting this paper with the title Characterization of Mitigation Schemes Against Timing-Based Side-Channel Attack on PCIe Hardware. Distributed embedded systems are a critical part of modern digital infrastructure. Autonomous cars are an example. Such systems consist of a host CPU, attached peripheral devices for robust computations. For example, AI workloads are offloaded to specialized peripheral devices for processing, like GPUs. Host CPUs are primary processing units and consist of PCIe interconnect and memory modules. There are other components that are part of host CPU, but we are mainly focused on PCIe interconnect. PCIe interconnects are made of root complex and memory controllers. Peripheral devices are connected to PCIe root complex and allowed to access memory modules with the help of memory controllers. What are timing-based side channels, and what is meant by the timing-based side channel attacks on PCIe interconnect hardware? PCIe is a high-speed interconnect in modern embedded systems, and nearly all high-speed GPUs and accelerators use PCIe interconnect to communicate with host computers. So figure 1 on the right side shows a host CPU with PCIe connected FPGA device and a GPU device. Now let's FPGA makes a memory operation, and let's say take t seconds to move a chunk of memory from host CPU to the FPGA. Now similarly, GPU makes a memory operation and it takes t seconds to move a memory chunk from CPU to GPU. Now in last scenario, for example, the GPU was performing memory operations and simultaneously FPGA requests memory from the host CPU. Although data is hosted on different modules on host memory and both devices are connected using separate cables, they share the PCIe hardware of the host CPU. Earlier data movement for FPGA takes t seconds, but now FPGA data have to wait for additional w seconds to read memory. This unwanted delay can be exploited to create powerful attacks and categorized as timing-based side-channel attacks. For example, the FPGA can measure the latency of memory operation, and if latency is t plus w, the FPGA can infer the presence of another PCIe connected device. A major requirement for timing attacks to work is shared hardware resources. There are two types of shared hardware channels in distributed embedded systems: persistent channel and non-persistent channel. Persistent channels store information for a longer time, such as caches, where non-persistent do not store information but assist with flow of data from one point to another point. Wires and interconnects are an example. So persistent channels are heavily studied for timing attacks and they are easier to target, and there is plethora of mitigation schemes exist, but non-persistent channels are not well attacked and mitigated, and they are difficult to target due to low timing variations. A recent work proposed an attack setup, and they demonstrate a timing-based attack that target PCIe interconnect hardware in a host and two peripheral device-based setup. Although it proposed attack setup and discuss mitigation schemes, but it do not discuss the performance implication of mitigation schemes. This paper explores various mitigation schemes against PCIe interconnect attack and characterize their performance impact using real-world machine learning algorithm on a distributed embedded systems. These timing attacks that target PCIe interconnect hardware leak sensitive information from security critical applications, and leakage of security critical information can be protected at system level, software level, and hardware level. At system level, a random noise injection scheme is used to obfuscate timing variations. Noise injection scheme is implemented in operating system. Similarly, Oblivious algorithm scheme is used to mitigate attack at software level, where timing patterns are modified to protect critical information. At hardware level, temporal isolation scheme, time division multiplexing is used to remove interference and eliminate timing variations. The efficacy of timing attacks depend on the timing variations between contention and no contention situations, where noise injection scheme obfuscate timing variation by introducing random noise. For example, adversary observe different timing for performing same operation that lead to information leakage. The noise injection scheme is easier to implement in operating system level, and this mitigation generates random traffic on PCIe hardware. This decreases the efficacy of attack for adversaries, but noise injection scheme have a serious security drawback. Literature shows that a smart adversary can denoise the channel using information theory concept and defeat the noise injection scheme. Noise is a common problem in information theory domain, where data is often transmitted over noisy channel. It have application in communication engineering. There are two famous approaches to denoise the channel: repetition codes and differential signaling. Repetition code is a simple approach that requires transmission of multiple copies of original information. The whole idea is to transmit enough copies of information that at least some reach destination without getting affected by external noise. On the other hand, differential signaling is another approach to remove the effect of external noise on transmission of information. Differential signaling requires a reference signal alongside of original signal, and later a difference is taken to retrieve the original signal. The idea behind this approach is that if there is an external noise, it affects both original and reference signal, where difference will remain same. Our evaluation shows that these denoise schemes work against noise injection mitigation and make noise injection scheme inadequate for practical purposes. A successful leakage of information requires that there must be a timing patterns in software implementation that is exploitable using timing variations. Oblivious algorithm scheme is a software level mitigation scheme that discusses the removal of such timing pattern to protect against leakage of information. One example is of machine learning algorithms where a repeated access to different size of kernels leak information about weights and structure of machine learning models. Oblivious algorithm can be implemented by adding dummy kernel and padding original kernel such that all kernel sizes remain same. The last mitigation scheme we focused is TDM. Timing variations are primary reason for such attacks, and controlled interference enable an attacker to exploit these timing variations. One solution to remove interference is temporal isolation of hardware resources. For example, temporally allocate PCIe hardware to peripheral devices. Based on this temporal isolation, a timed VN multiplexing based scheme is used to mitigate this attack. It slices time into T interval, and each T time is allocated to just one device. For example, for initial T seconds, the PCIe hardware is allocated to GPU, and only GPU is allowed to utilize resources. Similarly, for next T seconds are allocated to FPGA device, and this allocation is repeated alternatively. We evaluated these mitigation schemes on a real hardware. For host CPU, we have used Intel Core i7 that includes 4GB DRAM modules and run Ubuntu 20.04 LTS. We have used NVIDIA GeForce 1030 GT as a transmitter PCIe device and Xilinx VCU board as a receiver PCIe device. We have programmed FPGA with Xilinx DMA subsystem IP and used Xilinx driver for this DMA to make memory access and measure the timings. We use LeanET5 machine learning algorithm alongside MNIST dataset to measure the performance impact of these mitigation schemes. LeanET5 is a convolution neural network that is commonly used in distributed embedded system environment for automatic vehicle identification systems. It consists of 7 layers, and 3 of them are convolution layers that use 5x5 kernel size in each layer. To measure the performance impact for Oblivious algorithm, we added 2 dummy layers. For TDM modeling, we use TensorFlow board monitor tool to measure the time spent on PCIe hardware and later double the time to calculate the performance impact of TDM. To evaluate the effect of information theory denoising scheme, we use two metrics. True positive rate shows the accuracy of attack, for example, a percentage of correct identification of contention and no contention cases, and the discrimination index quantified difference between contention and no contention, and DI is based on mean and variance of contention and no contention latency distributions. To measure the performance impact, we use overall completion time of LeanET5 algorithm. Total time is divided into time to load the code and data into GPU device and time spent on the computations. We implemented noise injection scheme with low, medium and high random noise injection. Our evaluation shows that a high noise is sufficient to reduce attack efficacy probability to 55%, which is equivalent to guessing. Now an attack with differential signaling enabled show a efficacy of 82% under high noise, which is sufficient to develop practical attacks. We conclude that noise injection is not a practical scheme. We evaluated performance of Oblivious algorithm and TDM scheme using LeanET5 algorithm. We have used 3 configurations of LeanET5 with batch size of 16, 128 and 256. A small batch size requires repeated operation over PCIe interconnect, thus relatively more time spent on PCIe interconnect, where a larger batch size spent less time on PCIe interconnect. Our results shows that TDM have least performance impact, which is 6% for 128 batch size, where Oblivious algorithm have performance impact of 30% for small batch size, and impact grows to 2 times and 3 times for larger batch size. Overall, this work concludes that the timing attacks on PCIe hardware can be protected at system, software and hardware levels. Noise injection scheme can be denoised using information theory concepts and make system level schemes inadequate for practical usage. Our performance implication study shows that the TDM scheme have least performance implication but requires a modification in hardware. Oblivious algorithm is easy to implement at software level and works best where major time is spent on PCIe hardware. Thank you, and please let me know if anyone have any question.